This meeting is being recorded.
In this next section from the Chapter 16 worksheet on acid-base equilibria, we'll take a look at something referred to as polyprotic acids. So these acids have more than one proton, that is an acidic proton. So more than one acidic proton, we'll call these. So what does that mean? That means that they're going to have more than one ionization, more than one dissociation, and therefore they're going to have more than one Ka values associated with these polyprotic acids if they fully ionize. So depending on how many protons, that's how many Kas we're going to associate. So for H2SO3 here, we see after the first ionization, we get this product here. Our bisulfite ion, HSO3 negative, and then we start with that ion here, another dissociation happens, and then we get this conjugate base over here. So we can see the first ionization, significant amount ionizes something times 10 to the negative 2, and then during the second ionization, less of the proton that's still hanging on ionizes. So we can see some common first and second and even third dissociation constants shown here for different acids. So we have ascorbic, carbonic, citric, oxalic. We might work with any of these. Notice that sulfuric, the first proton, that's considered a strong acid at that time. So the Ka is so large, it's not even included on this table. It's considered to be, 100% ionized at that point, that first proton. But the second proton only ionizes this much with respect to this dissociation constant. So let's take a look at sample exercise 13 and see if we can figure out what we're asked for here using the Ka1 and 2 values in the table above. Note that we're going to have to do 2 or more ice tables. So do 2 or more ice tables with these polyprotic acids. So let's take a look at what that looks like here. So first we're asked in part A to calculate the pH of a 0.1 molar solution of carbonic acid. So we're given the formula. We'll look up the Ka 1 and 2s, and then we're asked to calculate the concentration of the carbonate ion in this solution. So we'll definitely have to do the second ice table because we need the second ionization to occur in order to get this conjugate base here. So let's start with the first ionization, H2CO3. Right, we add that to water. We can ignore that because that doesn't affect our equilibrium. And so after the first dissociation, we get this bicarbonate and hydronium. So we know initially we have 0.1 molar. Here we have 0, 0, minus 1, plus 1, plus 1. The ratio is still 1 to 1 for each of these, so we still just use negative x and plus x. So at equilibrium, we're going to have 0.1 minus x and then x and x. We're going to set this equal to our first Ka value for our carbonic acid. So that's 4.3 to the negative 7. And we're safe to continue with our approximations for now, not worry about quadratic formulas because that Ka value was so small. So that was that 4.3 to the negative 7. We're going to set this equal to our Ka expression. Again, we're going to ignore that x, assuming that it's so small. So we rearrange, we solve for x. So eventually we're going to have 4.3 to the negative 7 times 0.1 equals our x after we take the square root of both sides. So multiply these guys together, take the square root. We get our x equal in this first portion to be 2.1 times 10 to the negative 4 molar. And we know that this is our hydronium ion concentration. So we can take that value and set up a second dissociation here. So now we have HCO3 negative plus water. And now we get our carbonate ion plus hydronium again. So now we can plug in. We know that we're going to have 2.1 times 10 to the negative 4 here to start. We're going to do the same type of ice table. So we have 0 of this, we're going to have, this is our other x, 2.1 times 10 to the negative 4. So this is our initial, our change, our equilibrium. So minus x plus x plus x. So our Ka2 now, that's going to be equal to, if we go back up to our table, this very small number, 5.6 to the negative 11. Notice that most of the concentration of hydronium will probably be due to the first ionization, because that's much larger. This value was at 5.6 to the negative 11. We'll set this equal to our equilibrium, so 2.1 to negative 4 plus x. And then we have x here, and this would be 2.1 to the negative 4 minus x. All right, so we're going to see something very helpful happen here. Our first product is this. Our second product is times 10 to the negative 4 plus x over 2.1 times 10 to the negative 4 minus x. So what we're going to see is that these negligible x's will cancel out. These values will also cancel out, and our carbonate ion concentration is actually going to be equal to the value of our second weak acid dissociation constant. So that concentration will be 5.6 times 10 to the negative 11. And we're only going to need to use the hydronium ion concentration up here found after the first ionization to solve for pH. So I'll squeeze that in here. So we have, again, our carbonate ion concentration found down here. The pH will be found right here. And that's everything that this problem asks us to solve for. So our pH is about 3.68. That sounds good, being that this concentration is about -4 molar.